So let's go over a couple of properties of limits of sequences. So here's the setup. So let's say we have two sequences. So we have an A sequence and a B sequence. Let these both be sequences of numbers. And let's assume that they both have limits. Let's say that the limit over the A sequence is capital L, and the limit over the B sequence is some number capital K. Now there are a couple of things we can do. If you have a list of numbers, then you can construct new lists of numbers. You can construct a new list by, say, adding or subtracting the elements together. So this would give us a new list of numbers. So this is a new sequence, and then we can take the limit over this new sequence, and the limit of this is equal to L plus or minus K. So in other words, limits behave very well with respect to addition and subtraction. So the limit of a sum of sequences is the sum of the limits of the respective sequences. That's what this is saying. Maybe I'll write that not in words, but symbolically, so you can see. Symbolically, this says that the limit of A plus B is the limit of A plus the limit of B. Symbolically, I have to say n goes to infinity, give some subscripts. So limits behave very well with respect to addition. In fact, you were introduced to limits in Calculus 1, and you probably didn't like them because they're kind of abstract, and then you use them to define continuity, and then you also use limits to define the derivative. And, of course, calculating derivative can be very complicated. You have the product rule, and the quotient rule, and all these weird things, and you probably forgot about limits. But limits, in contrast to calculating derivatives, are actually very, very nice, because they respect all of the type of structure, all of arithmetic structure. So here we see condition 1 says that limits respect addition. We also have that limits respect multiplication. So that's the second property here. So if I have a list of numbers, I can construct a new list by multiplying all the numbers. So I can construct a new list where I just multiply them out. So the new first object is you multiply the first objects together. The new third object is you multiply the third objects together. The new 17th object is you multiply the previous two 17 objects together. That gives you a list of numbers. You can ask if you can take the limit of that. It turns out, yes, you can. It's just the same as the limit of the first sequence times the limit of the second sequence. So again, I'll just write that. So schematically, that says the limit of AB is the limit of A times the limit of B. Okay? So if you had such a rule like this for derivatives, that would be really nice, but I mean, we don't have that thing. So limits are super friendly, is all I'm trying to let you know. And similarly, limits behave well with respect to division. So assuming that the limit of B sequence is not 0, then this is just the limit of L over K. And here we have to assume. So we're assuming, couldn't decide. Assuming that K is not equal to 0. So again, this says symbolically that limits behave well with respect to division. So the limit of A over B is the limit of A divided by the limit of B. So these are three essential properties of limits. So limits behave very, 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 very well with respect to the arithmetic operations of addition, subtraction, multiplication, and division. So we can use these to calculate limits. So these are tools to calculate limits. So example, so here's an example. Let's calculate the limit as n goes to infinity of n plus 1 divided by n squared. So now we don't want to actually use property 3 here because the limits separately go to infinity over infinity. So we could take that observation and then take advantage of what's called L'Hopital's rule. But we don't need that. Instead, what we can do is we can just split the fraction inside the limit. So this is n over n squared plus 1 over n squared. And then we can just continue doing the arithmetic. So that's the limit as n goes to infinity of, that becomes 1 over n plus 1 over n squared. And now we can use the first property, which says that we can just distribute the limit. We can calculate on each term separately. So the limit over the first term, of course, gives 0. The limit over the second term also gives us 0. So we just add those together, and we get 0. So that is how we calculate limits. And I number this, but that's the only example I want to do. So these are just how we calculate limits, is we use these three properties. So again, if you have two sequences, and one of the sequences has a limit L, and you have another sequence, and that sequence has a sequence, say K, then the limits behave well with respect to all of the arithmetic operations.